code is actually not the full picture. It's the runtime behavior is what ultimately counts. And the runtime behavior also depends on dynamic effects, like variations in timing and interference between tasks. And these things are not visible or even defined in the source code. To get a full picture, you also need runtime monitoring. And you may ask, why bother? If my code passes the testing, well, all should be fine, right? Well, it's not that easy, actually, because these dynamic effects may cause a whole lot of different execution patterns under the hood, so to say. Many of these patterns are probably just fine, but some might be buggy and perhaps doesn't even show up in your testing. You can't really know. I will come back and explain a bit more what I mean by these execution patterns. But my point here is that the dynamic stability of your software design is really important for the testing and debugging process. And here's an example from our TraceAlyzer tool showing 4 different execution patterns. This is the same task in FreeRTOS in this case, just with different timing, different event orders. This is just from a very simple toy application. I could find 4 patterns directly in just a few minutes. I mean, how many patterns could there be in a more complex, realistic application? And I should mention that when you study real-time systems in the university, etc., we're taught that the logic of the application shouldn't be affected by patterns in the scheduling, etc. The RTOS is intended to take care of that. You have different stacks, etc., and the context switching makes it appear that the task is isolated. But this assumes that the task is really independent, that there are no functional dependencies on other tasks, and that there are no bugs that could affect this in any way. And you can't assume that. If we assume that the application is bug-free, why do we even test in the first place? So it's you really need to take this dimension into account. So how do you design an RTOS-based software to reduce or to improve the dynamic stability, to have fewer patterns, so to say? There are some things to think about. First, you should know that it's really difficult to do multi-threaded software development in general. This has been a known problem for decades. These kinds of bugs can be really tricky, and it's difficult to get this right unless you follow kind of best practices, the wisdom that has accumulated in the software industry. I have started on a list here with some advice that can be good to know, from very high-level things to more detailed things. And throughout the development project, there are a number of pitfalls and things to good advice to follow. And one thing, for instance, is in the very early phase of the project, when you select the processor, it's important that you have sufficient performance, and also that if it would turn out that the performance is not sufficient later on, that there is an easy upgrade path. Perhaps there is a slightly faster processor that is pin compatible, for instance. And another aspect is that your application will probably depend on base software from your vendor, like a middleware vendor or an RTOS vendor or a processor vendor. You don't write all the code from scratch. You have certain drivers or a board support package to begin with. And it's not certain that this software is perfect either. You really need to ensure that these critical base functions for operating on the device are of high quality and has the performance you need. And before you start hacking away and churning out a lot of application code, it's really important that you make sure you have a sound initial software design, that you have partitioned your application into suitable tasks, threads, and that they're communicating and interacting in a sound way. Otherwise, it might become a big mess after a few months, and the project might be prone to failure, actually. There are a number of best practices in kind of more detailed software design. It's important that the team members are aware of this and follow this throughout the project. If someone starts doing things their own way, disabling interrupts, for instance, to protect a critical section, and other team members are not aware of this, it could seriously impact the system performance. Another example is you shouldn't use busy waiting to have kind of a spin lock where tasks are polling something. Instead, you should, when designing with an RTOS, you should leverage the RTOS functions to suspend the task while waiting. That way other tasks can execute instead, and you avoid wasting CPU cycles. Interrupt handlers should be kept to minimal. You should do as little processing as possible within interrupt handlers and instead trigger tasks that can run on lower priority and do the job and that way you can still receive other interrupts. So you have better interrupt response time. When assigning task priorities, this is a really tricky field, actually a whole research field on its own. There are, for instance, methods like rate monotonic that you can use to assign priorities to tasks in a way that gives more confidence in the execution, so you can be more certain that the timing requirements will be met. For instance, in if you apply rate monotonic, which means that the priorities should be assigned according to the task rates, that is how frequently they execute. A task that executes every 2 milliseconds should have higher priority than a task that executes every 50 milliseconds, for instance. But to do that, you need to keep track on the periodicity of the tasks, of course. There are many more best practices like this. There isn't actually that much written in this area. There are a few books, for instance, by Chandler Bross and Richard Barry, the RTOS people, but they mainly focus on how to use specific features in RTOSes. I know that there is a blogger called Jacob Benengo that has started an initiative in this direction and written a bit about high-level best practices, how you should break down your design into tasks, etc. I'm planning to write a bit more on more detailed concerns in this direction. Another aspect is that you should make sure you keep track of the software evolution during the development, especially if you're a team of a few developers or more. If it's just you, then perhaps it's fine, you can keep everything in your head, but when the application becomes slightly bigger and perhaps you have 3, 5, 10 developers or more, then people will start doing things in their own way. And it can be difficult to overview this in the source code. You can actually use runtime monitoring to see this in runtime instead. Another thing is that you should make sure to detect and fix any anomalies you see in the software behavior as early as possible. because otherwise, when the behavior gets increasingly complex and these anomalies, if you will, these glitches that you're not quite certain why they are, they will accumulate and make things really difficult for you. And if you have important requirements on performance and timing, make sure to keep track of this throughout the project. Start with this as early as possible. Otherwise, it can be really hard to try to optimize this in the end of the project. Perhaps you have a task that needs to be able to run every 5 milliseconds, and it turns out that it takes 7 milliseconds to run the code. What do you do then? Perhaps you would need a faster processor that you should have found much earlier. Or perhaps you can optimize the software somehow. In general, many of these things benefit a lot or even require that you do runtime monitoring. You can't figure this out just by looking at the source code. So runtime monitoring, what does that mean? Well, there are different ways you can do this. This is nothing new. People have monitored their software since the dawn of time. Printf is a common example, that you insert printouts in your code at interesting locations. This is what I call application logging here on the right. And this gives you a kind of a semi-structured log. This is generated in the software. It's typically on a fairly high abstraction level. The overhead depends greatly on the method you use for the output. If you're logging over a serial connections running at, say, 115K bauds, then it might take milliseconds to output a printf like this. So then the overhead would be significant. This means that if you have that kind of logging, you shouldn't use a printf in any time-critical code whatsoever, like an interrupt or high-frequency task. Also, the actual printf method consumes a lot of stack and a lot of CPU cycles, so it's not very efficient. On the other end of the spectrum, we have instruction trace. For instance, using a Segger trace or an iSystem box or something like that, or a Trace32, you can capture data directly from the processor core on what branches and jumps that have been made and exactly what instructions that have been executed. The data you get is then very detailed on a low abstraction level. The overhead is typically none, because at least from the software perspective, it might be some minor bus overhead in some cases, but typically no overhead. The drawback is that you need special, quite expensive hardware. You need to have a cable and a box plugged in, and you need to have a board that is and a processor that allows for this kind of tracing. And also the amount of data you get can be quite overwhelming and perhaps too detailed. It doesn't give much overview. And in the middle, we have what we call software event tracing, or event annotations is another word for it. And this is something in the middle. It's still produced by software instrumentation, as in logging, but in a more structured way. Typically, you have instrumentation that the vendor provides in the APIs and in the RTOS, so you as an application developer don't have to add printouts. The abstraction level is more, say, a medium abstraction here. You get the information on things like context switching, important API calls, etc. But you can also combine this with application logging to get both medium and high level events. The overhead is typically less than application logging. Can be some overhead, and it depends greatly on the application, how many events you have, etc. And also the processor speed, but typically the overhead is quite small. And you don't need any special hardware, so you can actually keep this enabled in deployed systems if you like, or otherwise you can make it very easy for developers to use this. You don't need any special equipment. And once you have the data, then the question is, how can you make use of this trace data in an efficient way? And we have defined this concept of visual trace diagnostics to try to explain this. And this means that you combine event trace data with semantic analysis. That is, that you process the data in a smart way and take the meaning of these events into account, and also combine this with good visualization. This allows for usable, actionable insights throughout the development process. There are many uses of this. I mentioned selecting a processor, for instance. So there are several applications in both the very early design and prototyping stage, during application development, for instance, system level debugging, as I will come into soon, in verification, and also in deployment. Actually, we have a solution for monitoring deployed systems. Assuming there is some kind of connectivity, we can submit issues to our web service dev alert and alert you when there's a problem in the field. One example of this very early use case to profile the base software. I mentioned this a few slides ago, that your application will depend on important software functions provided by the vendor, like typically in a BSP or middleware, that are actually quite critical for the performance. It could be, say, a function for outputting data on a communication protocol, a communication interface. And it might be that your Ethernet connection is capable of 100 megabits per second, but if your TCP IP stack or the Ethernet drivers are not of good quality or not really optimized, then the theoretical hardware performance doesn't really matter. The drivers also needs to perform. I've seen many cases where vendor software from processor vendors, etc., are not that good actually. So it's important to check this. So you can use, for instance, TraceAlyzer to check the timing and also what's going on when you are sending and receiving data, for instance. Here we can see that we are sending and receiving data on a network interface. And you can see that there's a lot of activity here in between the events we have logged. It's not just a simple function, but they trigger other tasks in the TCP/IP stack that runs on higher priority and takes a lot of CPU time. So it's important to keep track of that. And now I have an example about how to use visual trace diagnostics for system level debugging. As you know, debugging can be really difficult when you see an issue in a full system test and you haven't isolated it yet to a single task or a single function for detailed debugging. In this very first stage, when you just see a weird symptom, you really need more information. You need to find clues so you can zoom in on the problem and analyze it more in detail. So in this particular case, we have a multitasking RTOS system that has a shared resource. There is a UART for output. So the system is outputting two different kinds of data from different parts of the application. You see this in the example here. We have one output like A, B, C, D, E, etc., and the other called other data. And normally they are on one line each, but in the middle you see that the first type of output, A, B, C, D, E, etc., begins, and in the middle it is preempted, interrupted by the other output. So the output from the system is essentially corrupted here. So where do you begin finding a problem like this? Well, we know that the UART is used. So we can record a trace in TraceAlyzer and make sure that we capture the UART output events, the writes to the UART. So we add an event in the driver, in the UART write function, to make sure we capture all these. And this is quite fast. Typically takes some microsecond or so on a 32-bit ARM MCU. If you would do this with an old school printf over a serial connection, it would be perhaps 100 times slower. So the impact of doing this kind of logging is really small. On the right side, you see then what we can see in TraceAlyzer. We see the two different tasks running. These rectangles here show the actual time between context switches, and the labels show different API calls that are made and our own custom events. So we can see that we have these two tasks that are outputting this kind of data. But okay, then what? Where is the error? How can we analyze the problem? Well, TraceAlyzer has a lot of support for what we call exploratory or top-down analysis. We have overviews, visual overviews, that allows you to spot anomalies at a high abstraction level, and then you can zoom in to see more details. So for instance, in this case, we take a look at how the response times of these tasks change over time. This is one example of a dynamic stability issue or a dynamic variation. We see on the right side that each of these data points here corresponds to one execution of either task. And all of a sudden here, we see that there is something different. And if we double click on this data point, we see the corresponding location in the task trace on the right side here, sorry. And we can see what happens. It's quite obvious in this case, but we see that this high priority task is interrupting, preempting the lower priority task. And it seems that it's doing this while this output is in progress. And that's the reason why we saw that this effect in the output. So to fix a problem like this, most of you know that you need some kind of synchronization, a critical section to prevent that the preemption occurs here. Typically you use a mutex for this. And a mutex is a type of semaphore for mutual exclusion. And if we do that, if we insert a mutex in FreeRTOS, you use a function called xSemaphore_take for this. And we can see in the beginning, the lower priority task begins to execute now. It takes this mutex, it locks it, and then it continues, performs the output. Actually, the output is performed throughout the function here. This is just logging the parameter. And after a while, we see that the other task is activated by the RTOS. It has been waiting for a while. And now it tries to take this mutex as well, but it can't because the mutex is locked. We can see that both tasks are trying to access this mutex. And you can also see that what happens here is that the lower priority task actually has the priorities changed by the RTOS. It increases the priority on this low priority task. And the reason for this is to avoid a problem known as priority inversion, where lower priority tasks may disturb higher priority tasks. I won't go into details there now, but and then you can see that once the low priority task is finished with the output, it releases the mutex xSemaphore_give. The priority is restored, and the high priority task is allowed to resume. And then it can perform the output. And now you can see in the output screen here from the serial terminal that we don't have this corruption problem anymore. You can read more about TraceAlyzer at percepio.com/TraceAlyzer. There is a free evaluation version you can register for and download. Get started right away. This is provided for FreeRTOS and other RTOSes, VxWorks. We also have a new version for Linux systems coming out soon. There is also a version for SafeRTOS that is provided by Wittgenstein. So please contact them if you would like to evaluate the SafeRTOS solution.
By the way, from 3 weeks ago, CITES is also representing SafeRTOS. So anyone that needs SafeRTOS information can contact us. Okay, good.
And then I would like to mention our new thing, Percepio DevAlert. This is about error reporting from deployed devices. Today, when you develop device software, I mean, we are not really used to the concept of having a connection, to have connectivity. So we test and test and test and hope for the best, basically. But in practice, there are always a few bugs remaining unless you spend millions and millions and millions of dollars on verification. I mean, even NASA have a few problems now and then. It's really difficult to catch all problems, and I mean, it's actually a theoretical impossibility to know if you have found all bugs, when to stop testing. So we can assume there always is a few bugs remaining, more or less. And it would be really nice if we could catch these as soon as possible, because the longer a bug is out there in the field, the more problem it causes, the more systems and users are affected. But with a connected system, some kind of IoT connectivity to, say, a cloud service, then we can provide trace data automatically in case of detected errors. So when you get a trace back from the field, then it's much easier for the developers to know that there is a problem in the first place, to be aware that, oops, we need to fix something here, and also to diagnose the problem. If you just get a report from a user saying that, oh, my system crashed, it can be quite difficult to find the problem. But if you get a trace and see that that task and that task were running and they were doing that and that just before the problem, then it can be much easier. We can't show you all the details, but we can show you a lot, and that helps you along. And by having this awareness and this diagnostics, you can hopefully fix the problem quickly and make an over-the-air update your devices before most of the users even notice there's a problem in the first place. So it's about minimizing the damage, if you will, of bugs that you do miss. So TraceAlyzer is for the bugs that you are aware of, that you know about, and DevAlert is for the bugs that you don't know about yet. Another benefit of this approach with DevAlert is that all the feedback you get is actually important input for your testing. Every bug you get back from the field is something your testing has missed. So that's really important feedback, so you can improve your testing to avoid that similar issues occur in the future. And this can be used for any kind of problem that you can detect in your software. Could be software assertions that fails, like sanity checks. It could be hard fault exception handlers, watchdog timers, stack overflow detected, out of memory, or even that you have more proactive warnings that, for instance, your stack usage have exceeded 90% or something like that. We're also planning to add support for more more proactive reporting or statistics. For instance, how an application is used by the users, what features that are used and how often, and if there are, for instance, usability problems. Say that you have a device with a certain setup wizard that users are expected to perform, and perhaps 50% of the users fail because it's too complicated or difficult, not explained properly. Then it can be important to know that. You can learn more about DevAlert at percepio.com/devalert. So to summarize this presentation, we have Percepio TraceAlyzer for trace visualization and analysis in the field. This is more intended for individual developers, but there are also ways to collaborate around TraceAlyzer. You can share traces with each other, etc. This is a desktop application with a traditional software license that runs on Windows and Linux. We have built-in support for Sega J-Link, ST-Link, a few other debuggers, but you can also adapt this for your own custom setups and stream traces over network connections, etc. It's quite powerful. I will give you a more hands-on glimpse of TraceAlyzer in a moment. And the Percepio DevAlert is about error reporting from the field. It's more of a service provided to product organizations doing IoT devices. There is a cloud service that handles the data and notifies users, and it's powered by TraceAlyzer and AWS. Yeah, that's my last slide, but I was actually thinking of showing you a bit more hands-on as well, what TraceAlyzer is capable of.
John, can you please go through the mechanism on how the software is working? What is needed in order to make it works?
Sure. So the question was if I could show how it works. Sure, I can do that. So here is TraceAlyzer, to record a trace, we need this software trace recorder for FreeRTOS integrated in our system. You can find it here. There is quick start. There is a getting started guide here in the user manual. Go into this section, FreeRTOS. And there's actually a better one on our website. Let me show you that instead. If you go to percepio.com and then you resources, getting started, a quick start guide for FreeRTOS. So here is a guide and some explanation of how it works. I can just explain this briefly. In the FreeRTOS kernel, there are about 100 different trace hooks available at strategic locations in the kernel code, like this one here. And these are preprocessor defines that by default are empty and doesn't produce any code at all. When we include our trace recorder library, we define these definitions so that they call our trace recorder and log events. And you can also add your own events like this one to do application logging. So you find the trace recorder library in the installation here, and you need to add a couple of C files, make some modifications to your FreeRTOS configuration, etc. It's not that difficult. And then there are two ways of using this: either snapshot mode, where you record to a RAM buffer, and then you can read this RAM buffer at any point and just take the snapshot and display it. You only need a few kilobytes of RAM for that, actually. but the traces you get are quite short. Or you can use streaming mode, for instance, with a Segger J-Link or IAR. And in that case, the data is transferred continuously, and you can record very long traces. And if we go back to TraceAlyzer, just let me show you briefly how this works. We can take a look at the settings now.
Can I ask a question?
Sorry, I have to...
I saw that you use both RTT and SWD. There are some pros and cons. I mean, which is better for work with TraceAlyzer?
I'm sorry, I had some audio problems. Could you repeat the question?
Just a second. When I saw that RTT and the SWD, there are some. Which of them is better for TraceAlyzer?
Doesn't matter.
Doesn't matter.
Yeah. It depends. The important thing is that you have your same setting as you use for your debugger, your IDE. So if we take a look at, if you have streaming configured, you can record a live trace like this. So now we are seeing live display of the system behavior. So here are task execution. We're looking at 500 milliseconds here. And this, we see here the amount of data that is transmitted. It's not that bad, about 50 to 100 kilobytes per second, but that can vary a lot depending on the application. This is a quite small application. And here we have a couple of views available in this live mode, CPU load, for instance. We can zoom in, etc. And we can even freeze a view if we like. We set this to unsynchronized. We can actually zoom in and see more like that. And then when we stop the recording, the trace is actually already loaded into TraceAlyzer. So now we can use all these 30 different views and get more insight. So this is the trace view showing things like task scheduling, interrupts, API calls, and what we call user events, that is application logging. And now we only see 2 tasks here, but that's because we have hidden a few of the tasks. If we select this option here, we can toggle this setting and see all these columns, but they're empty here. That's why they were hidden. And if you're interested in a particular message queue, for instance, you can click on this event and see all things that are happening on this message queue. We see that there is a task called control that is trying to read data here from this queue, but there's nothing there, so it fails. But then all of a sudden this HMI task wakes up and sends data to the queue. We can see that a message is added. And a second message is added. The numbers here are just sequence numbers that we assign to the message. We don't show the contents by default, but you can add extra logging for that if you like. Like that. The CPU load shows you the distribution of CPU time to different tasks and threads and interrupts over time. So here we have a vertical timeline like this, or a horizontal timeline, sorry. And if you want, you can double click on a peak like that and see the corresponding area and see what's going on. There is also another view that is quite useful called user event signal plot. And this is a generic data plotting function or view that takes the data provided in user events and show them graphically. So here we have logged a PID motor controller, for instance. So you can see the set position and the current position, the actuation, and the motor response here. So to do this, we have simply added calls to this vtrace printf function and logged the data we're interested in. If you have a lot of events like this, it says here, zoom in to show 1005 events, and that's because there are too many labels, too many events to show all in this view. Either you can zoom in like this, or you can change the filter. Perhaps I'm only interested in these user events, then I can hide all the other things like that and get more a better overview.
כנסו לי לאטנדי. למה הם נכנסו לפרזנטר? אתה לא רואה אנשים שנכנסו לפרזנטר? דותן, הצטרף מאוחר, הגיע לפרזנטר.
Did you have a question?
Yes, I have a question. Can you hear me?
Yes.
Yes. So, does this tool can also show memory usage the system?
Sure. We have both actually heap and stack usage here. So if we start with heap usage, this is okay. This trace doesn't. No, here we go. So here we have malloc and free events. So here is the initial allocations of the task stacks, I believe. And then there are some additional events here, malloc and free.
Mm-hmm.
And if you double click on these labels, you can actually get more information like this. And I believe we actually have a memory leak in this example. Yes, you can see that the allocation level slowly increases here.
Mm-hmm.
And if you're interested in finding memory leaks, you can use this filter here, show remaining only. And this way we only show the events that, or the allocations that have been allocated but not yet freed. Mm-hmm. So these ones are probably fine. Those are the task stacks, etc. But here we have a couple of allocations that still remains. It doesn't have to mean it's a memory leak, but it could be.
Okay.
Another type of memory usage is stack usage. And that is shown like this. So this shows the amount of remaining stack for each task. And this is done by sampling the stacks periodically. So the time resolution is limited. I think in this case it's about 10 milliseconds between the samples or so. But the y direction, the amount of margin is exact. So here we can see that as the system executes, the amount of the margin of this for the stack usage goes down as more and more code is executed. And we can see here that there is 140 words remaining for this task. So here we are wasting quite a lot of memory actually. And here we have much tighter margin.
Mm-hmm. And one more question about CPU usage.
Yes.
You have also CPU logging?
Yes, that's what you see here. This is a summary of the trace. It's based on the tracing of context switches. So it's not statistical profiling like sampling, but it's actually measuring exactly. So you see in the trace view, we know exactly when things are executing, and this is a summary of this trace data. And you can see it visually like this, or you can get it like a report. Where is that? Here we go. So you can select what tasks you're interested in, what properties, and then you can get an HTML report like this with statistics. And you can see things like CPU usage on average, execution times of the tasks, response time, that's the total time from the task is triggered until it's finished. The execution time is kind of the net execution time, the time excluding disturbances and things, periodicity, separation, things like that. And all the extreme values here, minimum and maximum times, they are actually linked to the trace. So if you're interested in this worst case or this highest response time here for this task, you can click here and find it in the trace like that. And in this case, it was nothing dramatic. It was simply a long execution time. In other cases, it might be because of other tasks that preempt or interfere. Let's see if I can find an example like that. Yeah, here we go. We see here that this task is actually not running here. This shaded area is the time it's waiting to get processor time. So it's waiting for 84 milliseconds, and then in the end it's running for 123 microseconds. So this is a very high disturbance here on this task. If this task is important, perhaps you should have a higher priority, for instance.
Okay, thank you.
Any other questions?
Yeah.
Yes,
I would like, you hear me?
Yes.
I would like to ask, do you have support with TI DSPs, SysBIOS, for example?
Not SysBIOS. That's nothing. Not we have. We have not implemented support for that yet. What we are planning is to provide a generic SDK that allows you to integrate TraceAlyzer recording with basically any system. We have been talking about that for a while, but it is planned for development this fall. So that will require some manual integration. You need to call certain functions at certain events, etc. But it will be very generic, and all functions should be supported that way.
I see.
The
Okay.
reason we do it like that is there are so many RTOSs and middleware libraries out there that it's impossible for us to support all and keep them updated. So we need to make a generic solution.
I see. And one other question, what about ThreadX support?
Sorry, what did you say?
ThreadX.
ThreadX, yes, we have that. ThreadX is supported. We use, in that case, we don't use our own recorder library, but we use actually the one provided by Express Logic that is already a part of ThreadX, or Microsoft in this case. ThreadX is supported. They have a limitation though, that their recording solution is only snapshot mode. You can't do streaming yet, but that is something we are also planning to improve.
I see. Thank you.
Thank you.
I have a question.
Yes.
Do you hear me?
Yes.
I want to try to make measurements profiling based mostly on hardware compatibility or some semi-hosting.
I'm sorry, I don't hear you. Could you adjust your microphone or something? It's very...
Yes.
Do you hear me?
Yes, much better. Thank you.
So the question is, if you are profiling mostly based on hardware capabilities or some sort of semi-hosting, which of them?
It's not semi-hosting. What we're doing is... now we have an echo as well. The way it works is that the recorder library has a RAM buffer, and this is when you do streaming, this RAM buffer is read in real time by a J-Link debug probe, for instance, or is sent over a network connection or something like that. Semi-hosting typically means that you halt the target system and let the debugger read the data in the background, and then let the system resume. But for ARM cores, you don't need to halt it. That's why Segger has provided this RTT function that allows for reading out data in real time without disturbing the execution. On ARM, there's also another way we can do streaming, and that is the SWO interface, or ITM. In that way, we can just write the data to a register, and it goes out over the debug channel.
So you actually really coupled with ARM architecture. I mean, chips.
Yeah, we have some integrations with ARM, but it's not exclusively for ARM. You can also use, the recorder has a concept that we call stream ports, and that's basically a header file that defines how you output your data. It's only like a preprocessor definition that says, I want to output using this function. So if you have an Ethernet connection or some other interface you want to use, or perhaps you have a flash file system, you can write it that way instead. So it's quite configurable. We're talking also to other processor vendors like Sci-Fi, for instance, about supporting their solutions.
It's RISC-V?
Yeah.
Okay.
But TraceAlyzer in general is not very hardware specific. We're interested in methods to output data, but TraceAlyzer doesn't really care about instruction sets and things like that.
Okay, thank you.
Thank you. Any more questions?
Yes.
I have a question too. I would like to ask, I was wondering if I could use this this TraceAlyzer on a Zinc ultra scale in order to trace events from all the CPUs that are inside. I'm talking about the A53, which are 4 cores, for example, and 2 cores of R5. Is it possible to synchronize the events that firstly it would be to record them, but then to synchronize the events that are coming from different CPUs, and then to look at the big picture and analyze things that go between CPUs?
Yeah, that is something we have been talking about, and we can do that on Linux. If you're running Linux on some Cortex-A cores, we can see them all together. We have support for the Cortex R5 with FreeRTOS, for instance, but we can't show them together yet. We're also working on support for the Microblaze core. But yeah, we don't have any way to show different operating systems at the same time. That will require large changes in TraceAlyzer because it assumes there is just one operating system. But that's something we are aware of, and it will probably come in the future.
And I have another question. I
Yes.
looked at the ordering options, and I saw that that it is a permanent license, not locked. And if, for example, I decide to buy one for Linux, which I would need for A53s, I would also need to buy another one for FreeRTOS to trace R5s, or is it possible to get a single license to trace them one at a time?
Well, technically you would need a license for both, and then I guess it's a matter of between you and CiteSys to agree on the price for that. It's TraceAlyzer for Linux is a very different product compared to TraceAlyzer for FreeRTOS, at least when it comes to the kind of back-end integration. It's completely different traces. It shares the same front-end and visualization, but the Linux work has taken over a year of additional work now. So, in general, we keep the different RTOS integrations as different products, but we don't have any restrictions on per project or so. So I mean, if you buy TraceAlyzer for FreeRTOS, you can use that for any FreeRTOS project.
Thank you.
I have a question.
Yes.
How we can estimate what is the impact of the analysis over the real-time performance of the
I can't say a specific number. I mean, 5.
No, I mean,
it depends on it's an interesting question, and it depends on a couple of factors. The faster processor you have, the less impact typically, and the more events you're recording, the more dynamic events, the more dynamic complexity in your application, the higher impact, of course.
Yes, I understand, but every time
typically, if a ballpark number is somewhere in between, say, 0.1% in a very good case, up to maybe 5% in a bad case, it's somewhere in that region, a few percent. It is typically not noticeable, but you can measure it. I mean, it adds a couple of microseconds here and there.
Okay,
yeah.
So for sure, when I run in without the analyzer or with the analyzer, I can be sure that my behavior, if I come to analysis, some racing problem or something with very acute timing, I can be sure that when I run with the TraceAlyzer, I don't get impacts on my timing that can change my behavior.
No, we can't guarantee that. And TraceAlyzer will, as long as we are using software tracing, it will change your behavior a little. But in most cases, it's no problem. But if you have a race condition, then software tracing is not the best solution. Then you need hardware tracing. We actually have, we are working on an integration with a trace emulator that will provide this later on. So if you're actually hunting a specific race condition and it's a matter of microseconds here and there, then software tracing is not the best method.
Okay. And the second question, when do you estimate the streaming option for TradeX will be available?
I can't say that right now. We don't have any specific plans for that yet.
Okay, thank you.
But since Microsoft acquired Express Logic, of course, this has increased the priority for us.
Okay, thank you.
Anything else?
Okay, if there is no more questions, I would like to thank you, John, for this technical overview.
Thank you.
People who need more commercial information can contact me in CITES. So thanks a lot, John. And,
thank you.
Have a great day.
Thanks for your time.
Thank you for your presentation.
Thank you.
Thank you.
Goodbye.
Thank you. Bye-bye.